Okay, welcome everybody. Thanks for coming. This is the week 3 webinar. So this webinar, we're doing 2 chapters, and 2 chapters usually means it's easier than if we're only doing 1 chapter, just to let you know. Or it means there's nothing big coming up this week, and there isn't. So we're gonna be doing 2 chapters today, and let me share my desktop to talk about what's going on. Okay, so we'll start out today using, oh, you know, let me plug in my mic just a minute. Better sound wise. So we'll start out today with question and answer, as always. So I'll be answering questions. I'm going to talk a little bit at the beginning about the project, just because you should be thinking about it and about some of the issues that people have had. And I want to make sure that you get these down. Then we're getting into discrete and continuous random variables. So we're doing chapter 4 and 5, as I mentioned, and chapter 4 is about discrete variables. Chapter 5 is about continuous variables. So we got to figure out what's what. Then after that, we're going to get into expected value, which turns out to be really useful. Comes up all over the place in the real world. Not like reading news articles, but more in making decisions. And I'll talk about why and how, and also understanding what's going on. Then we'll talk about a binomial distribution. And that's a distribution basically of how many yes answers you get when you have a survey with yes, no questions. So that's what a binomial distribution is going to be. Then we'll get into continuous random variables. So we'll talk about what is a probability distribution with continuous random variables. Looks very different than discrete, as we'll find out. And then we'll get into one very special case, and that's called the uniform distribution. We're not necessarily doing the uniform distribution because it's like really important, it happens all the time. We're doing it because it's really easy, and you want to start easy before you get hard. So it's the easiest distribution you can handle when it comes to finding probabilities. So that's why the uniform distribution is the way to go. And we'll have some example questions, and then we'll talk about if you have a uniform distribution, what does it mean? What's the standard deviation, and how do you find a z-score? So that is the plan of the day. Today, I want to mention a couple things about the project. So at this point, you should be well into your project. Hopefully, you've already come up with your idea. And I strongly recommend reading my feedback on each other's, not just yours, but going through, the bottom of the project discussion forum and kind of read through where other people have stumbled and I kind of helped them out, or whether people made it and I said, great, looks good, it's going to work. So that you don't make mistakes if not too many mistakes. And I want to mention a couple mistakes that I'm seeing. And one is about stratified sampling. So first thing, you cannot even do this project if you haven't identified what your population is. So that's really, once you've come up with like your survey and your idea, what you want to ask, the next thing you want to do is you want to say, who is the population? And that might be all Americans, that might be all Californians, it might be all students at the college. And you might want to restrict it to adults. That's a possibility because you're not asking children. So it might be American adults, for example, but you want to definitely think about who the population is. That's very important because that'll help you on coming up with a survey technique. So most of you, not all, but most of you are going to be doing stratified sampling. So that means once you've decided on your population, then you have to do research. So stratified sampling does not mean that you survey the same number of people in each group. Okay, very important. I've seen that in multiple people actually made that mistake already in their proposal, and I let them know don't make that mistake. So don't survey the same number of people of each type. You want to survey a proportionate number of people of each type, which means that you have to do research to find out the proportion of the population of each type. So if you're doing ages, for example, you probably want to do the research before you decide on the age brackets, because you're not going to be able to do some, whatever age brackets you feel like and come up with it very easily. It's easier to do research, find out what the age brackets are in the population, and then use that as your stratified sampling, and you can do the quotas from that. Any questions on that idea? Any questions? Okay, so that's just a few things. Again, I wanted to mention what kind of were stumbling blocks when I was helping people out on the project discussion board.
Actually, I do got a question.
Sure.
All right, so let's say that I found out the population, there's 18 or 20% is going to be 18 to 23-year-olds. Now, how do we randomly pick, since we're using, my group's using Facebook, how are we going to randomly pick those 20% from our Facebook friends?
Okay, it's a really good question. So the first thing, and if you remember when I was going over the project, beware of the word randomly, because the answer is you can't. Okay, the project does not require you to randomly pick, because you can't do that. So it means you're going to have bias. But in this project, the project does not have a requirement that there can't be bias. What the requirement is you have to identify and write about the bias. Does that make sense?
Yeah.
Yeah, so if you're picking your Facebook friends, they're kind of more like you, and you got to decide, well, how are you different from the population? Do you know what I mean?
Mm-hmm.
And so you write about that. And then you say, yes, there's bias. You admit to the bias. You get points for admitting to the bias. You lose points for pretending there's no bias. Does that make sense?
Yeah.
Yeah. So that's hopefully that answers your question.
Yeah. Nice.
I want to mention one more thing. That part of the write-up of the project is that you have to do research and find out the percentage of the age groups or whatever. You need to actually, in your paper, you need to cite that reference. So where did you find those percents? Okay, and a link is fine. Could be online. I'm okay. I'm not strict in terms of like an English teacher would, make you have all the formalities and citations. I just want to see a citation. Sound fair? Yeah. So that's the requirement. Is you have to have a citation. And there's all kinds of different types of citations. I don't care, as long as I can easily see what you got it from. The main thing is just showing that you actually use something instead of just made it up, because making it up's not allowed. Any more questions? Any questions about anything? Okay, I just wanted to let you know, again, you still have, I don't know, week and a half or something, week and 2/3 before the project is due, but don't wait till the last minute. Okay, in fact, don't wait till the last minute on anything. We may have a windy weekend, which means that you could lose internet on Sunday, which means you should get all the work done on Saturday. You know what I mean? Don't wait till Sunday night to start working on stuff, because I got multiple emails Monday saying, could I have more time? And the answer is no. I don't give more time unless it's asked for by Friday. So I just want to remind you on that. Don't procrastinate, get it done a little earlier. Okay.
All right. I have a question also, sorry. So what is the best way to survey your population, in your opinion?
Well, it totally depends on who the population is. So there's a group doing, I know we have a group of hospital staff. So theirs is different, because they're going to go to the hospital and survey the people that they're surveying, because they can do that because they have to be there anyway. If you're like me, which means you're stuck in your living room, although next week's different, I get the vaccine, but that's a whole different story. Then you're going to want to do it online.
So emailing, for example, college students.
Yeah, emailing, Facebook, whatever your connections are is the way you want to do that. If you're doing college students, if you're doing college students, emailing, you could even ask your instructor to maybe, post and see if someone will answer your question. You know what I mean?
So we could do that here or in the forum?
Yep. Yeah, you could email each other. You have all each other's email addresses, right? You have a little mail to thing button. I think you do. I have it, and I think you do too, right?
Yes.
Yeah. So you can just mail the person, hey, can you please answer my survey?
Okay, thanks.
Yeah. And again, we're in weird times because of COVID. Normally we'd have a lot better sampling with less bias, but life is tough now. And I will not allow you to get COVID or give COVID to someone because of this project. That's against the rules completely. Got it? But yeah, so you're gonna have biases. The important thing is you talk about the bias. Okay, it's allowed to have bias when you talk about it. Other questions?
Yeah, I had a question on one of the questions on chapter 3. Should I just post it in the Q&A discussion board, or
That's probably best, unless it's a quick one I can answer now. But if it's like a long question, the posting in the Q&A board, by the way, not the project discussion board.
yeah,
So that'd be the Q&A board.
okay,
Yeah, and also after this, I have office hours, and you can ask me then too, if it's a longer
Okay.
one. I have an hour to work with. Yeah. Okay, and that's at 11. So. Okay, other questions? Okay, if there's no questions, I want to talk about discrete versus continuous random variables. So the one thing is that this chapter and most of the rest of the chapters, we mostly focus on quantitative data. But it turns out there's kind of two main varieties of quantitative data. There's discrete and there's continuous. And I'm not going to give you a true formal definition. And I'm going to be saying this a lot in this class. And the reason is calculus is not a requirement. So the formal definition requires some very serious mathematics. And I can't do that. But I can't assume you have calculus, and hopefully you're glad about that. So what I'm going to do is I'm going to give you more of the idea of the difference between discrete and continuous instead of like a full, formal definition. So let me start out, and you definitely want to start with discrete. So definition, kind of. Right, to you, it'll look like a definition, is the following. A variable is discrete. When I say variable, and maybe I'll say random variable, because that's what we're doing in this class. So, and when I say variable, that's usually the answer to a survey question, or it could be the result of collecting data, using measurements, that kind of stuff. That's what variable means. It's all the different answers that can happen in your study, and it is discrete if it can be listed, if all the possibilities can be listed. And that is possibly with ... Okay, so let me give you some examples. There's a lot of them. So a survey question might be things like, how many times did you go to the market over the last 30 days? Okay, can you list all the possible times that someone could have gone? Sure. Could have gone 0 times, right? Could have gone 1 time. Could have gone 2 times. Could have gone 3 times. Okay, and I keep writing, and I could maybe get to 10, and then I can go ... And that would be a discrete variable. Does that make sense? Okay, so let me give you another one. I'll even pop this in. I'll let you put it in the chat box. Let me ask you, how many siblings are in your family? And by the way, it's at least 1 because you count. Put it in the chat. Tell me how many siblings there are. Okay. Wow, 7. Big family. Okay, so in particular, you'll look at these things. Could you list all the possible answers? Yeah. Here's a tough question. Are they 1, 2, 3, 4, 5, 6, 7, ... Told you it was a tough question. Let me put mine in. Mine's a modern family. So I have 4.5 because I have a half sibling, and that can happen. But you can't have a third sibling, by the way, a 1/3. So basically, it's 1, 1.5, 2, 2.5. So you could have fractions, but you can't have all possible fractions. You can only add some fractions. Does that make sense? So you have to list. You have to be able to kind of list them all. Okay, and sometimes with a table. Okay, and that's a definition. And let me give you the other definition. And you'll see why I started with discrete, because the only nice way of doing this without using intense math is what I'm about to do, is a random variable is continuous. Oh, I should say a quantitative. I told you I'm only doing quantitative today. A quantitative random variable is continuous if it is not discrete. Okay, so that would be something like exactly how much do you weigh? Okay, and you can't list every possible weight, even with ... because, for example, I weigh 171.3572, etc. pounds. Okay, so the point is that the weight is something that you can measure. It could have fractions, and any fraction is possible. Okay, so things like weight would be continuous. Okay, or things like how much time did you spend in the shower the last time you took a shower? That's continuous because that's something that you're measuring. It could be fractional. It's not discrete. Okay, one of the nice things about English, actually, and I actually never noticed this until I taught, believe it or not, I taught English in Japan. And that is that if it's discrete, the second definition is continuous. Yeah, maybe I'll make it red if you want. If you weren't seeing it. I don't know if that helps. There we go. Does that help? Okay, so the second definition is definitely about continuous. Okay, it was written, but again, putting it in red sometimes helps out. So one of the nice things about the English language is that we actually have different grammar for discrete versus continuous. So for discrete variables, the question usually starts with how many. And for continuous, it usually starts with how much. Right? How much do you weigh? Right? How many pairs of socks do you have? So how many pairs of socks do you have is discrete. Do you see that? Okay. How much time do you spend every day on the internet? That's continuous. Do you see? So one of the nice ways of doing it is to say, is it how much or is it how many? That works almost all the time. Not, I'd say 100%, but close to. Any questions on these big definitions? Any questions? Okay, so
Can you
again,
just repeat? I'm sorry. Is it discrete is how much and continuous how many? Is that what you said?
one more guess, the other way.
Sorry.
Yeah, maybe I'll even put that here.
Can you actually just, yeah, thanks. Sorry, I
That
just
would be
missed it.
how
I'm
much?
making
How many?
for my kids. How many?
And this
Thank
guy
you.
would be how much? Okay, and that's a nice way to kind of hear it and see it, because that works most of the time. Okay, there are other questions where you don't say either of those things, but if you can say how many, that's pretty much always going to be discrete. And if you can say how much, that's almost always going to be continuous. Any questions on that idea? Okay, so we're going to start out with discrete. So when you have a discrete distribution, what that means is you can list all the items. So for a discrete distribution, we can write out a probability distribution table. Okay, so we can write out a probability distribution table based on the outcomes and the probabilities. Any questions on that idea before I give you some examples? Okay, so I'm going to start out with that distribution table, and then I can continue on with the same example. So that's our plan, is that you can write a table, because if you can list things out, that means you can put them as the headers of the table. Any questions on that? If it's continuous, you can't. You can't write it as in a table. So let me do an example, and I thought I'd pick one out of the book. And I feel comfortable doing out of the book. You know, you never want an instructor that like reads out of the book, but this is different because I wrote it. So it is me. I'm not just copying someone else's stuff, and it's a game. I know not all of you are from Tahoe, but skiing is one of our main industries. What's our next biggest main industry? Might be first in terms of money.
Gambling.
Gambling. So I created a gambling game. So let me show you the game, and we're going to play it. We got to scroll down a bunch. This was fun to code. So this is the be the player or the casino expected value game. And what it says is you will be given the rules of a randomly selected hypothetical casino game. Then you're supposed to compute the expected value, and based on the result, choose to be either the player, the casino, or the player. Okay, then 10,000 games will be played, and you will win or lose the amount of money, of course, in theory, and that's how it's going to work. So I'm going to go through the steps, and the first step after I hit next game is to write out the table. So let's do that. I'm going to hit next game. And by the way, it randomly grabs games. And just if you play this game, just load. I programmed it so that 50% of the time you want to be casino, 50% you want to be the player. So beware of just saying, well, it's always going to be the casino. I wrote this game, so trust me. It's just, that's the way this one works. That's why it's in theory. Okay. By the way, at the casino, are there any games that you can actually win at consistently? Or not consistently, but statistically? Any guesses?
Craps.
Nope. No, you can't win statistically at craps. If you play long enough, you'll lose. Any other guesses? Blackjack? No. And I'll tell you something about blackjack. The reason why you can't win, even if you do all the numbers, is me, personally. They actually hired me, and I helped them change the rules so that people like me can't win, using expected value, using what we're doing today. Okay. Of course, very sophisticated. I can't get into all the details, but so you can yell at me if you lose at blackjack. It's my fault. Okay. But there is a game, actually. There's one game. There's one game that you can actually win at if you're very good. And that is poker. Do you know why? That's because you're not playing against a casino. So if you're playing at a table with a bunch of dummies, and you're like really using statistics, you can win in poker. And you have to have a good poker face. So that's the only one because you're actually winning against them. Casino takes a percent. Okay, so just let you know. But all the rest of the casino games, no. In the long run, you won't win. Well, we're going to talk about the expected value, and it will be negative. But this is fictitious. So let's hit next game. Okay, here. The game involves a wheel that has 89 equally sized number slots. Okay, so it's basically roulette. Okay, it's kind of roulette, except, the numbers are a little weird. So it has 89 equally sized number slots. The wheel will be spun. If it lands on a 1, the player wins $27. If it lands on a 4, the player wins $26. If it lands on 18, the player wins 15. If it lands on 62, the player wins 12. Otherwise, the player loses $1. Okay, so we're going to eventually decide whether we want to be the player or the casino. Any questions on the question? Any questions on the question? Okay, so what I'm going to do, I'm going to do it on pen first so I can leave this screen and go to the other screen, is I'm going to look at all the different things that could happen. So one thing that could happen is you can win 27. Okay. Another thing that can happen is you can win 26. A third thing that could happen is you can win 15. You could also win 12. Or you could lose $1. Any questions? And there are 89 different things that could happen. All right, so now I want to go to a place where I can start doing some work. So what I'm going to do is I'm going to make a table. And in this table, there's going to be 2 rows. And you could choose whether you want to do rows or columns. I'm going to do rows just because on this screen it'll look better. So I'm going to do 2 rows. And the rows are going to be the value, the amount of money you win for the first row. And the second row will be the probability of that occurring. Got it? And there were 5 different outcomes that could happen. So I'm going to make a 2 by 6 table because I want the first thing to just be to talk about what's going on, and then the others are the numbers. Oh, interesting. They call it 6 by 2, but it isn't. It's a 2 by 6. All right, so we're going to have, the first thing is I'm going to use X as my letter to represent how much you win. And P of X is the probability of that outcome occurring. So let me stop. Any questions on this? So we saw from the game that you can win 27. You can win 26. You can win 15. You can win 12. And you could lose $1. What number should I put in if you lose $1?
-1.
-1. So note, losing is a negative number. And that's common. It's common to have both positive and negative numbers with expected value. I mean, it doesn't always happen. So for example, if you wanted to look at the expected value, if you wanted to look at a probability distribution table for number of children women have, then you're not going to get negative values. Hopefully you all agree. But that would be, by the way, number of children a woman has is definitely a discrete distribution. You can't have, 2/3 of a child. It doesn't work. Okay. Now the probabilities, the first probability is going to be 1 over 89 because there's one number that made you win $27. So I'm actually going to type in 1 over 89. And I get 0.0112, 4 decimals enough, 0.0112. And the good news for this example, which is not true of all examples, is that the probability of winning $26 is also the same, because each of those had one thing that made you win. So that's also 0.0112. And in fact, let me just copy and paste. And the same thing for 15 and 12. How do I find out the probability of losing?
Subtract the 4 from the total 89.
You could do that, but in theory, it's a little easier actually. Is what is the probability? What should they all add up to? If I add up those decimals,
1.
1. So I could take 1 minus the sum of those 4 numbers. Do you see that? So I can take 1 minus, and that'll be 4 times, because there were 4 that were all the same, 0.0112, and you get 0.9552. Any questions on that? Anybody lost?
So since you said that they all have to equal 1.
They have to add up to 1.
Oh, they all add up to 1. Would that happen with any other distribution table we have? They always add up, or they always should add up to 1?
Sure, because there's 100% chance that something happens, right?
Yes. Okay. Thank you.
If you list all the things that could happen, there's 100% chance that one of them is going to happen, right?
Yes.
If not, then you forgot to list something. And
okay. Thank you.
Mistake. Yeah, so you will always get the sum to be 1. So if you have one of them that's difficult to figure out, you find the rest of them and subtract from 1. Okay, and that's really easy to do. Any questions on this? Okay, this is called a probability distribution table. Let me put this actually in red, because that's an important word, or phrase, I guess is the right thing. This is called the probability distribution table for this situation. Okay, and because it's discrete, we can do that. Sometimes you have a ... I will never give you a question on homework or on your assignments or on your exam where you have to compute a probability distribution table that has an infinite number of possibilities with ... So don't worry about it. Sound good? But I could give you one that has 5 different possibilities. I think that's fair. Any questions at all on this? Okay, I want to mention a bunch of other types of places where you'll see this kind of thing. In fact, one, I just read about it last week. I was going to do it, and then I realized the math was a little too hard, so I couldn't do it and have you guys follow. And that was what we did last week. What probability did we figure out last week? What was one
Lottery.
of the lottery? The lottery. Oh, by the way, what's the probability that that ticket I showed you last week is a winner?
0.
0, it lost. You know, I don't know if you watch the news, you know it lost because no one won, right? So don't come to my house and kill me and take this ticket, or you're just stupid. Got it? Because that ticket is worth nothing right now. It's sitting in front of me. I might buy one today because it's gotten, we're going to find out about expected value. The expected value has gone over what you pay for now. It's kind of cool. Or that's pre-taxes though. Okay, so just a note. So lottery is the same idea, because last week I showed you how to compute the probability of winning the grand prize. But you can win all kinds of other things too with the lottery. If you get all but one of them, you win $1 million or something like that. So you can write down the probability distribution table for the lottery and decide whether or not it's worth playing. Does that make sense? Because there are only a finite number of types of wins that you can have. And there's only one type of loss, and that is you lost your $2 that you had to pay for it. So you can write that for the lottery, and that works. Any questions on that idea? Okay, and I just read a news article It was very interesting, that said that the expected value actually goes down when the winnings get way too high. You know another reason? Okay.
Because more people buy.
Yeah, more people buy, and if you win and someone else wins, you split. So if 2 people win, you only get half of it. 3 people win, you only get a third of it. And that happens a lot once it gets up these numbers. Just let you know that, a warning. Okay, but it was interesting. I read that. That was a news article about expected value. And we'll be talking about that next. That's what we're going to do now. Let's talk about expected value. So first thing, let me give you this definition in idea of the expected value. So given a probability distribution, a discrete, okay. Let me ask you, put in the chat box, put a yes if you've had calculus and no if you haven't. My guess is we're going to be all no's, but we'll find out. I might be wrong. Okay, I'm just seeing no's. All right, so I'll let you know something. You can actually do an expected value for not continuous, but you can't do it without calculus. There's no chance. You can't even talk about it. So I'm not going to talk about it. Pre-calc doesn't count, by the way. You need calculus. So you can't even talk about it without calculus. So I'm not going to. But I will let you know we're only going to do expected value for discrete probability distributions. So given a discrete probability distribution, the expected value is the number such that if you conduct, or if you select, or actually do many trials, okay, kind of like buy many lottery tickets or playing this game many times, however it might be, then it will be likely that the average outcome will be close to the expected value. So I want to highlight some important words here. Many. So this does not work if you just do a trial. So if you just buy one lottery ticket, the expected value is pretty meaningless. Okay, but if you play often, that's different. Likely means that it doesn't mean it's always going to be true, but it's usually going to be true. And it turns out the higher the many is, the more likely it happens. And then close to, you're not going to get exactly that number, but you're likely to get close to that number. And I guess I should say average is another keyword. Okay. So for example, the expected value for the lottery ticket is probably right now, pre-taxes, is probably around 5 cents positive, which is a good thing, by the way. It means on average you're going to make 5 cents. Okay, but how often are you going to make 5 cents if you pick one lottery ticket? If you buy one lottery ticket, how often will you make 5 cents? This is a very easy question, by the way. Not one.
Depends how many you buy.
Doesn't depend on anything. Now, you only buy one ticket. I already said that. And how often are you going to make 5 cents? Never. You can't win 5 cents in the lottery. Do y'all know that? Yeah, there's no 5 cent win. There's $1 million of winning and stuff like that. There's the $2 loss, but there's no 5 cent win. So just because you have an expected value of 5 cents does not mean you expect that value to happen. It just means that if you buy many tickets or if you try it many times, then you're likely to have an average that's close to that number. It's very different than saying you're just going to get that number. Any questions on that? And also, because it's an average, even if something can't happen, you don't do any rounding because it can't happen. So if the expected number of children Americans have, which is true, is 1.7. So American women, by the way, is 1.7. Then you don't need to round 2, even though it's impossible to have 1.7 babies. Because as soon as you say expected value, you're talking about average. Any questions on that? Okay, so then there's a formula, and I'm not going to get into, you can read in the book and get the formal formula and all that. And basically you're multiplying the probability times the value of X and then adding them all up. That's the formula. So it's 27 plus 0.0112 plus 26 plus times 0.0112, etc. You just keep going until you're done. That's the expected value. But that's a hard way of doing it. What's the easy way of doing it?
Maybe adding the top numbers and then adding the bottom numbers.
Much easier. Much easier.
Yeah.
It's too obvious, so you're probably not thinking about it. You put it into my expected value calculator. Doesn't that sound easier? And you let it do it for you. Do you agree that's easier? Yeah. So what I do need to do is write down, because we have to change screens, 0.0112 and 0.9552. Okay, so what I'm going to do, so I'm going to go here. And what I want you to do, because I am hoping you can, I tried to make the calculator really easy. Tell me what number I should pick, which calculator number.
6.
Yeah,
6.
number 6. Yeah, again, there's no trick questions here. So it's number 6. And not only did I try to make it easy in terms of words, I tried to put it in the order of the class. So we're here at number 6. And by the way, guess what we're doing in week 12? Week 11, sorry. It's not a trick question. Week 11, we're doing ANOVA, number 25, the last one. So again, I've put this calculator in order to try and make it as easy as possible. And again, if you have any suggestions, I'll make that happen. And I keep doing that. I keep making it easier and easier because students want to have a good suggestion. I hadn't thought about it before. So if you could think of something to make it easier, I'll do it for you. So we have to make the probability distribution table. Okay. For reasons because of the formatting, I made it as columns instead of rows. This particular program doesn't do well with rows. So we had 27 for our first X, and our probability was 0.0112. In fact, I'm going to copy that because it happens a bunch. Okay, and then the next one was 26. Same probability. And then 15. Same probability. And then 12. Same probability. And then -1. And that probability was 0.9552. Any questions? Okay. And hopefully you all know what button to hit next.
Calculate.
Calculate. And there's the expected value. Okay, so the expected value is negative 0.0592. All right, so do you think this is a good game? This is a game you want to play a lot. Yeah, why not?
because the casino has a 95% chance of winning.
That's not true either.
No?
No, 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 no. No, no, that's not a probability. It's a value, not a probability. Let's go back. Let's go back to the definition. So here's the reason. It's because if we play many times, then it will be likely that our average loss will be close to 5 cents per game. Do you see how you can take this definition and turn it into interpreting what the expected value means in this situation? And notice that many, likely, average, close to, those never go away. Those words have to be there. And on the exam, by the way, if you do not put all those words in, then I will take off points because those are necessary. Okay, so the negative 0.05 is not a probability. It's the amount that you're likely to lose close to if you play many games on average. Notice I threw all the words in. The order of which you put the words isn't so important, but you got to put all those words in. Any questions at all on this? Okay, what do you think the expected value? Any guess on what the expected value when I was 21 years old for a experienced card counter was in blackjack? Per dollar? For you play a dollar? Any guess? No one wants to guess? It's about 4 cents positive. So and you could play a lot of games per hour in the casino. So at the time it was about 4 cents positive. So I played many games. I'd sit there for 6-7 hours sometimes. That's why they eventually told me they'd kill me. But I play for that many hours. How many times do you think I didn't end up winning by the end of the day?
Very few.
Never. Because if you play many trials, then it's likely you're going to be close to. So if you're at 4 cents, sometimes I'd win on average 3 cents, but never 0. I'd always make money, and sometimes more than others, but I always made consistent amounts of money. And that's why they figured it out, is that I always left winning. Okay, and that's what you want to do. And I know you're not going to be card counters, but some of you said you're interested in having a business. And what you need to do is you need to decide what your expected value is. You know, because customers have different things that they could end up doing, you know, buying this or buying that. And you find out the probability that each of the customer is going to buy this and that and the other thing, and then see what your expected value is per customer. And if it's negative, then don't go into that business. If it's positive, it needs to be, of course, higher positive than your costs. You have to pay rent and all that kind of stuff. And, you know, you have to pay salaries of the people working there. So for good business, you got to make sure that you have a positive expected value. And if you have a positive expected value above and beyond the cost, then that's a good business. That's a business that can actually make it. But if your expected value is negative, it's a bad business. The hard part is you have to come up with the probability distribution table, and that takes business research. And this is not a class in business research. This is a statistics class, but you should get that in your business classes, is how you can come up with what customers are likely to do based on advertisements and things like that. Any questions on that idea? Okay, so this is used everywhere. Okay, it's even used in the health industry, because what you want to do is you have some choices on what kind of treatment to give, and you want the treatment that has the highest expected value. Okay, and that expected value might be, or the lowest expected value for the number of days it takes for someone to recuperate. So then you want a low expected value because you want it to not take so long to recuperate or to get better. Okay, so it happens, this is a really important subject all over the place. The reason I chose this kind of silly gambling one is it's easy to put in a table. But in the real world, it's a little more complicated, but you can do it. Any questions on this example? Okay, I want to show you one more thing since we calculated already. I popped in, not this one. I popped in the standard deviation. The standard deviation is 4.56. I'm going to go to the nearest penny. That's our units are in dollars, by the way. So that means that 4.56 is the standard deviation for the amount of dollars in this game. Now that is a very high standard deviation, especially if you compare it with the expected value. The expected value is like 6 cents negative, and the standard deviation is $4.56. So what does that tell you? What if you have a high standard deviation, what does that mean? It's the same standard deviation idea. Any guess? Any thoughts?
There's a big difference in the numbers.
Yeah, there's a big difference. There's a big fluctuation in the outcomes. And you're not usually going to be that close to the expected value when it comes to individual games. Do you see how that works? So standard deviation is for the individuals, and it says that there's a high fluctuation. So by the way, we already chose to be the casino, right? And if you're a casino, then you just flip it to positive. You multiply by -1 if you're the casino, right? So it says that, yeah, you're going to, on average, if the player plays enough, likely win very close to 6 cents a game. Do you see that? But the standard deviation is high, so you better make sure that people are playing a lot, because if people are only playing one game, you may end up coming out a loser badly. Do you see that? Okay. On the other hand, if you play enough, then the expected value, because of that many games, then you can be pretty confident. So you got to make sure you have capital. If there's a business, for example, you got to make sure you have capital, enough cash in your in your pocket as a casino industry to be able to give people money when they win. Do you see that? Because there's a pretty decent chance that you're going to end up losing a lot on the first game. But then by the end of the day, that's not going to happen. Okay, just a note, because this is another example. It's a Tahoe thing, so sorry if you're not from Tahoe. But I used to teach a class called the Mathematics of Gambling. It's a fun class. And I had a student in it, and I talked about expected value. And at the break, this was like a 5-hour, one-day class. And at the break, she came to me and she said, well, I got to tell you, I'm in charge of the casino. And what you're saying isn't right, because you saying that we have a positive the casino has a positive expected value, but we've been losing for a month now. What do you think I told her?
That in let's say 6 months, it might be closer to the value.
No, see, a month at a casino, we're talking thousands and thousands of games played. So I told her to look at your cameras. And the next day came out.
Someone's stealing.
They caught the ring and they all went to prison. So I actually sent people to prison by using expected value. I mean, I sent them indirectly. The police are the ones that sent them, but I'm the one that helped the casino catch the cheaters, because it's not going to happen if we're talking many, many thousands. Okay, it was kind of cool that it happened, and they deserve to go to prison. I mean, if you cheat like that, you should go to prison. And it was a whole ring of dealers and players cheating, and they got caught. But they wouldn't have got caught if I didn't help this person, this casino manager, with the mathematics, and let her know that no, this isn't going to happen. It's not even 1 in a billion chance that this would happen randomly. Once it's many, many thousands of games. Do you see how that works? Okay, so that's expected value and standard deviation. Any questions about it? Okay, I'm doing one example in depth instead of many, because they're all basically the same. You're given the possible outcomes and their probabilities. Sometimes you have to compute them. And you pop it into a table, and then you put the table this way in your calculator, And the calculator will give you the expected value. And by the way, if I play the game now, I want to be the casino, right? And if I play the game enough times, the casino should win. And here we go. Just won 319 games, played 10,000 times. That's $319, 10,000 times. And if I play enough, then the average winnings should end up being very close to the expected value. Occasionally you see a negative, but most of the time it'll be positive. And then if you play enough, it'll definitely be positive. Any questions on this? Okay, and I even made a picture based on the game. That's what the game would kind of look like. Except it would have 89 slots. So, you know, so if you've been in a casino, you know what you're looking at. Any questions at all on the expected value idea? Okay, so let's move on to the next big topic. So we have a bunch of topics, or three topics. So the next topic is binomial. So if you have a survey, it doesn't have to be a survey. It could be a survey by asking people. It could be a survey of collecting data, or seeing if you win or lose, whatever it might be, where it is a yes/no question. Then the probability distribution of the number of yes answers is called a binomial distribution. I'll make it capital. Okay. Okay, and note that for this, the probabilities can't change. Of yes must stay consistent. So that means that if you're doing a survey, then you don't want to spend if you're doing survey of, I don't know, Biden's approval rating, you don't want to do it for 3 years because that's going to fluctuate based on, what's going on in the news. Okay, so you want to make sure that you're doing it kind of all the same day so that the probabilities don't change because of some external stuff. Notice this is discrete because the number of yeses is either going to be 0, 1, 2, 3, 4, etc. So you can ... it. Okay, what I'm not going to do is the math. And you're going to hear that a lot from me because in this case, the math is too hard. And I'm not going to go there. So, but you are responsible for being able to recognize a binomial distribution, being able to use the calculator, and being able to come up with answers. Okay.
I have a question. Just
Yeah.
so the word binomial means to name. Why is that?
Yes or no.
Oh, got it. So
Yeah.
there's two possible outcomes.
Yeah. And when I say yes, no answer, it doesn't have to be yes, no answer. It could be dead or alive. That's fine too. But you can always turn it into yes, no. Do you see that? So it could be something like that too. It could be, I don't know, human or not human. That's a yes, no, but the answer might be yes. It might be human. Do you see? But as long as you turn it into yes, no, that counts. Any questions on this definition? Okay, so it's an important definition, and it comes up a lot because the yes, no question comes up a lot. And you're often interested in probabilities. Okay, any more questions? Good questions. Okay, so once you have this, then you can start doing probabilities, and we can talk about that. So for example, let me just do an easy one. Okay, suppose you toss a coin 30 times. Find the probability that it'll come up heads (15 times). By the way, the expected value of heads would be 15, right? Because if you toss a coin 30 times and you're not cheating, then your average would be 15. Do y'all agree with that? But what's the probability of it being exactly 15 times, right? You expect it to be 15, but that doesn't mean it's likely. Any questions on the question? Any questions? All right, so what I'm going to do is I'm going to go to the calculator. And I need to go back to the regular calculator. And what number do you think I'm going to use?
7.
Yeah, this is 7. Okay, we're going in order. As I told you, this class goes in order. All right, so in this case, it says, what's the lower bound and the upper bound for the number of successes? Well, in this case, we want exactly 15. So to be right about 15, it can't be lower than 15, and it can't be higher than 15. Any questions on that? Our trials were 30. And we got to do a probability, sorry. Probability was 0.5. Again, if it's a fair coin, 50% chance of heads, right? And it's about 0.1445. You may not have expected that, because if there's a 50% chance of getting heads and you flip 30 times, you would say that's probably pretty likely of getting 15 heads, right? Actually, it's not that likely. Okay, it's not likely to get the expected value. So it's about 14% chance. Any questions on that example? Okay, let's do another one. Suppose that 8% of all Americans are left-handed. If you survey 25 randomly selected Americans, find the probability that at least, actually, let's go at most 3 will be left-handed. Okay, is this binomial?
Yes.
Yeah, you're either left-handed or you're not left-handed. Do you agree? So it's binomial. And we want, the hardest part about this whole piece of this section is understanding the word at most and words like that. If it's at most 3, then what does that mean? What does at most 3 mean?
It's a discrete distribution or
Discrete. But
probability.
what's the lower and upper bound? Because that's what we need for the calculator.
The low,
What's the lower and the upper bound?
Would the lower be 0?
Yeah, lower is 0 and the upper would be
3.
3. Okay, a lot of people have trouble with that. I know you didn't, but a lot of people have trouble with that. Trust me, because I give tests and I see what happens. So at most is 3 or less. So you got to read those words and get them right. Okay, whereas if it said at least 3, then it'd be 3 or more. If it said more than 3, it'd be 4 or more. You see how that works? Because 3 is not more than 3. So you got to get used to those words. And I can't do all the examples, but I can do some of them. So let me write these down. We have 25.08 and 0 to 3. And we just got a calculator and the rest is easy. Once you've got it kind of decided what to do, 0 is a low, 3 is the up. Number of trials was 25, and the probability was 0.08. Any questions? And there we go. So there's an 86% or so chance that if you select 25 people at random, that at most 3 will be left-handed. Any questions at all on how these work? Okay, again,
I have a quick question, and it's kind of back on the last one. Just where the low is 15 and the up was the 15 on the heads and tail.
Right, that's because it was exactly. So with the last one, it's again, the hard part of those words. So come up heads 15 times, not less than 15 times, not more than 15 times, but 15 times.
Okay.
So if it's 14, did it come up 15? No. If it's 16, did it come up 15? No. So the low is 15 and the high is 15 because anything other than 15 doesn't count. Does that make total sense?
Yeah.
Where this one had the word at most, and that changes everything. Yeah, so that's the hard part, is reading those words. So be very careful about reading every word. Okay, now let's move on to continuous distributions. If it says 4 or more, then, okay, so in the example we just did, the upper would be 25. Do you see how that works? Because if you survey 25 people, you can't have 26 be left-handed. So 25 would be the highest. It's logic, and logic's not always that easy. So let's do continuous. Okay, so a few things about continuous. First thing is you can't list them all. Okay, that's what the whole point, the definition of continuous is all the possibilities are not listable. Okay, what you can do is you can have an equation and you can have a graph. So let me do an example. And this is where it gets a little messy and hopefully it works. Sometimes Google gets mad at me. So I hope it doesn't. So I'll know in a moment, it'll be a while before I know. So I'm gonna have an x-axis. And I'll have a y-axis also. I don't always draw the y-axis, usually don't need to. What you're gonna draw is what's called the probability distribution function. Okay, I'm not the best artist, by the way. Okay, so this is an example of a probability distribution function. Okay.
This was in the calculator? I'm sorry.
No, I'm just using Google to draw.
Oh,
This is a lecture. Yeah. I won't require you to draw because I can't make that happen.
oh, good. I'm like, wait, how are we supposed to get here?
But you're supposed to be able to watch. Can you watch? That's all I care about.
Yes.
Okay. And you can draw it in your mind. So the idea is if you want to say, let's say the numbers here. Let's say that's 4. And that's 7. That's 10. Just putting some numbers in. And let's say you wanted the probability that it's between 7 and 10. Then what you're going to do is the following. So you're going to draw a line up like that. And draw a line up like that. And then going to fill in everything in between. Except it didn't let me. Let's try again. Okay. So the area that I just drew is the probability of something being between 7 and 10. And that's how continuous distributions mean, is that if you want the probability between two numbers and you have the distribution curve, then the area under that curve is the probability. Any questions on that?
Is this the only way to show that type of probability then?
In a picture, yeah. So the area between 7 and 10 is the probability that 7 is less than x is less than 10. Okay, and just to note, the probability of being exactly 7 is 0, because the area of a line is always 0. So area of being exactly anything is always 0. So the probability of being 0 does not mean it can't happen when it comes to continuous variables. That's a little weird to feel, but it's just the way it is. But between numbers, then you usually won't get 0. Any questions? Let me save and close and cross my fingers. This does not always work.
Can you just repeat
It
the
works.
phrase that you just said? The probability of being 0.
The probability of being exactly any number is always 0 with continuous distributions. And that's because the base of what you're doing is always going to be 0. And remember, base times height. So I want to let you know that none of you have the ability to solve the problem I just drew, because you don't know how to find areas on curves that look like that. Do y'all agree? Because you said you haven't had calculus. On the other hand, there is one kind of area that you are all responsible for knowing how to find. What's the area? The area of what should you know how to find? Can't find this one, but there are examples where area can be found. Starts with an R. Yeah, rectangle. So you should all know the area of a rectangle formula, which is base times height. So let me give you an example. Okay, and let me first write down a definition. A distribution is called uniform if the, I'm going to write PDF, probability distribution function, so that's that curve that I drew, is horizontal. We call that a uniform distribution. And what that means is that anything of the same length is going to have the same probability. So let me give you an example. So I got a little time. Suppose that the time, let's say the second hand, at the end of the webinar is uniformly distributed. By the way, uniformly is the adverb of uniform. Uniformly distributed between 0 and 60. Find the probability that class or the webinar will end with a second hand between 11 and 23. Any questions on the question? Okay, I don't pay attention to the number of seconds on the clock. I pay attention to the minutes, but not the seconds, by the way, when it comes to when we finish the webinar. So it probably isn't uniformly distributed, because if you don't pay attention, then anything's just as likely. All right, well, how do I do this? Key is I draw a picture. Okay, so we're going to 11:23. So let me draw a picture and let me insert. Hopefully it'll let me do this. Sometimes it hates me, but last time it liked me. Insert a drawing. All right, so since it's uniform, what I can do is I can draw a rectangle, because uniform distributions look like rectangles. Do y'all agree? So I'm going to label 0 for the beginning and 60 for the end. And I want to be between 11 and 23. Oh no, that's bad. Let's try again. Okay, and this isn't drawn perfectly to scale, but I tried to do my best. Okay, then what I'm going to do is I'm going to put a little vertical line at 11, and a vertical line at 23. And I want the area, so let's go to scribble. And I want that area. Any questions on the picture? Well, so the probability that 11 is less than X is less than 23. That's what we want. And by the way, less than or equal doesn't matter, because equal has no probability anyway. Is equal to the base times the height. I'll write BH, because it's an area of a rectangle. Isn't that beautiful? Okay, I need to find this height. Well, I know that the probability of being between, what is the probability of it landing between 0 and 60?
1.
1. So I know that if I take the base of the whole rectangle, which is 60 minus 0, and I multiply it by the height, which I'll call h, then that's equal to 1. And then basic algebra gives us that the height is 1 over 60. So now I can come up here and I can work it out. The base is going to be 23 minus 11, because that's how far it is from 11 to 23. And the height is going to be 1 over 60. And what I get is what, 12 over 60. And 12 over 60 is 0.2, I believe. Yeah. You can put in a calculator if you don't want to use your brain calculator like I did. Any questions on that example?
So the base and the height is always going to equal 1.
The base times the height of the large rectangle will always equal 1. Does that make sense? Yes, I wanted to make sure the wording was right. Okay, let's do another example. So suppose the weight of a medium-sized apple is between, I'm totally making this up, by the way, so don't get mad at me if that's not how heavy an apple is. I'll even ask you, how many ounces do you think an apple weighs, a medium-sized apple? That way I don't get in trouble for guessing wrong.
4 ounces.
4 ounces. Okay, so let's say it's between 2 and 6 ounces. Anything smaller than 2 ounces, we'll call that tiny. Anything bigger than 6 is a giant apple. Got it? And is uniform. Find the 34th percentile for medium-sized apples. Any questions on the question? Any questions? Okay, so what I'm going to do now is I'm going to draw a picture. So let's do that. Let's start a new page. Now I'll draw a picture. And again, this is Google Doc. So if you ever want to draw something using Google Doc, this is how you do it. It's not a requirement for this class, but it's good life skill to know, I guess. So what I'm going to do is I'm going to draw a rectangle. Always a thing to do when you have a uniform. The keyword is uniform. If it doesn't say uniform, don't use uniform. Okay. Then it went between 2 and 6. Any questions on that? And we want the 34th percentile, which is a little past a third. So I'm going to draw a line somewhere around here. I don't know exactly where it is. Okay, now is this 34, this value of x? Right here? No, I don't know this value of x. And if you don't know it, you call it x. What I do know is the following. I know that the area to the left of x is 0.34 because that's what it means to be the 34th percentile. Any questions on that? All right, let's save and close. Now they have the picture, I can answer the question. So remember that the probability that x is that we're between 2 and x well, that's equal to 0.34. But that's also equal to the base times the height. Any questions on that? All right, let's get the height first, just like I got before. Well, I know that the height, that the area of the whole rectangle is 1. So I know that 6 minus 2 times the height is equal to 1. So the height is equal to 1/4. Any questions on that? So now I know that 0.34 is equal to the base. Well, what's the base of this rectangle? I'm looking for an expression, not a number. That's a hint. What's this base of this rectangle over here? This piece.
An X? No.
Well, it's not just X. That doesn't quite work. Okay. If you want to find the base, then what you do is you want to find this length. If you want to find a length from one number to another, you subtract. So it's going to be X minus 2. Any questions on that? And the height was 1/4. Any questions on that? All right, we're looking for X. So we get to do your favorite thing in life, I think, is algebra. Y'all love algebra, right? What do you have to do both sides? Not sure. Multiply by 4. Okay, not multiply by X, multiply by 4. So multiply by 4, I get 0.34 times 4 is equal to X minus 2. 4 times 34 is 136, right? So we get 1.36 is equal to X minus 2. And now, hopefully you all know what to do to get X by itself.
Add 2.
Add 2. So I add 2. 2 plus 1.36 is 3.36. Equal X. Any questions on that? Okay, now I need to do the very last thing because I don't have that much time, just a couple minutes. Actually, before that, I'm going to give you a secret word and then I'm going to continue on. The secret word is discrete. Discrete is chapter 4. So to pick one of them. So that's the secret word for the day. And now I'm going to go on and do our last bit, and that is the mean and standard deviation for a uniform distribution. For uniform distribution, the mean, actually distribution between A and B, between two distributions always have a left and a right. The mean is so you want to see the problem? Hopefully that's enough. So the mean is going to be, and now we're going to have a formula. Mean's easy, actually. So the mean and the median the same because it's symmetric. All right, after I'm finished with this, I'll show you the picture. The mean and the mean are the same because it's symmetric. And that is the following. It's the average. And hopefully you remember the average of two numbers. You take the first number, you add the second number, and you divide by 2. And by the way, that's the mean. Do you remember what letter we use for mean? Mu. I know you can't type it in your chat box. So mu is that, and I better make this bigger because it's too small. Google's not good about that. Yeah, it's better. And now let's make it back to small again. And the standard deviation is, and now the mean kind of makes sense. Take the average, that gives you the mean. I will guarantee that none of you would come up with the standard deviation formula if I asked. That's a guarantee. So sigma is equal to the square root of the fraction parenthesis b minus a squared all over 12. And
Are you
that's,
saying we're not responsible for doing this?
you're not responsible for proving it,
Okay,
or even knowing or even vaguely understanding the proof.
okay, great.
Okay. Mu, on the other hand, that's just the average of the numbers, right? That makes sense, right? Standard deviation, even if you've had my calculus class, you still wouldn't understand it. So there's a lot of very advanced math that's behind the scenes. And the good news is if it's hard, then you don't have to do it. Sound good?
Sounds great.
Okay.
Thanks.
You do have to know how to use a calculator to add two numbers and divide by 2 or to take a square root, that kind of stuff. But that's not so hard. So just to, I don't know, let's find the mean and standard deviation for this example where you had between 2 and 6. It's not hard. So for the apple, then remember the apple was 2 to 6. Then what I like to do is I just copy and paste, and A was 2. B was 6. 2 plus 6 is 8 over 2 is 4, which is obvious because the middle of 2 and 6 is 4, right? And then the standard deviation is going to be b minus a squared over 12, all under a square root. B was 6. A was, 6. A was 2. So it's the square root of 6 minus 2 squared over 12. And I guarantee you're going to want a calculator to do this. And I could do 6 minus 2 in my head. That's 4. 4 squared is 16. So it's root 16 over 12. And you just do root 16 over 12. SQRT, I think, always works. And that was 1.15 about. So for example, if you wanted a z-score, for a 5-ounce apple, what would you do? Remember? So the formula for z-score was x minus mu over sigma. X is 5 minus mu was 4 over sigma, which is 1.15. I could do 5 minus 4 in my head. Hopefully you can too. And then, so it's 1 over 1.15. Or we could just do 1 over like that. And you get 0.866. So by the way, is a 5-ounce apple an outlier? What do you think?
Is it no, because it's not bigger than 2?
Right. No, because it's not bigger than 2. It's definitely not an outlier. Not unusual at all to see a 5-ounce apple, given the fact that we have a uniform distribution between 2 and 6. That was all the total made up. So please don't, go to the store and get mad at the, clerk because their apples are too small or something, because we made these numbers up. All right. Well, we're out of time. So I'm going to stop the share, and I'm also going to stop the recording.